Right, good morning everyone. Thanks for attending today's webinar. Today, as you probably already know, we're going to be covering safe motion. This is one of the more obscure subjects, and that's why I've chosen it, to be perfectly honest, not one that's covered very often. So basically what we're going to do today, sorry, I will introduce myself first. I'm Andrew Maskell, I'm one of the account managers. I've only done one of the webinars previously before today, and basically I'm going to be running you through this subject. Now this is our usual page. Basically, if you can't hear me, if the sound's bad, please let us know. You can type questions using the toolbar to the right hand side of your screen. We've got my colleagues Jamie Thomas and Jason Reed in the background there that can answer your questions during the webinar. If it's something we can't answer immediately, we'll certainly do that following the webinar today. Following this, you'll get a link to this recording a few hours after the webinar's finished. If you want copies of the slides, that kind of stuff, then just let us know. There probably isn't any handouts I'm aware of, but certainly you'll get copies later on. So just bear with us on that. So the agenda today, we're basically going to cover the fundamentals of safe motion and the main aspects that need to be considered when designing and implementing these types of applications. We're not going to cover everything to do with the standard, obviously. We're going to focus in on some of the main aspects. So the agenda's there, so we'll start to run through. So basically, we look at the traditional safe state on a machine when it is stopped and there is no movement. But of course, this can impede productivity. And so while absolute standstill is still necessary in the majority of cases where a risk assessment permits and the required technical measures are feasible, such as safe mode selection, safe speed detection, and so on, a case can be made for allowing equipment to run without necessarily stopping it during human machine interventions, such as machine setting up and fault finding. So BSEN 61800-5-2 is basically a product standard. So it specifies requirements and makes recommendations for the design and development, integration and validation of safety related power drive systems. And I'm emphasizing that, and I've highlighted it because lots of acronyms appear in this as usual. So just be aware of what that actually stands for when it's used. So in terms of their functional safety considerations. So yeah. So safe motion. The term safe motion is interpreted differently depending on where you stand. So drive manufacturers will look at this as being safe motion that's drive integrated, whereas controller manufacturers associated with external solutions. So third-party solutions, for example, such as safety relays and safety monitoring. So looking at the issue independently, we can establish that the term safe motion only refers in the first instance to implementation of a safe movement. So motion is described through the kinematic variables acceleration, speed and distance. And again, I've just put that word there because if I'm absolutely honest, it's not a word I use every day, but these words do pop up in the standard. So it's just interesting to know what they actually mean again. So as far as potential hazards are concerned, torques and forces also will play a key role with regards to safe motion. The above variables are covered by the safety functions listed in the standard. The implementation of safety-related monitoring is heavily dependent on the sensor technology as well, so we'll look at that. The sensor technology used within the drive technology is generally not safety-related and must be monitored for faults. So, for example, a critical status would occur if the encoder was unable to supply a signal due to a defect. So while power is applied to the motor and it's accelerating, this obviously would cause quite an issue. When you examine the application of the fail-safe principle within classic safety functions, initiation of the safety function causes the outputs to shut down, and this is called a safe condition. If safe drive functions are used, an application may become more dynamic rather than static, so there is some movement there. In safety technology, dynamic is understood to be the ability to adapt the safety functions to the changing detection zones. So the functional safety requirements for variable speed drive specified in 61800 will open up new horizons on this issue and just basically gives a different look at things. The main requirements of safe drive systems in terms of dynamic safety are safe monitoring of the kinematic variables such as acceleration, speed, distance, short reaction times to reduce stopping distances, and variable limit values, which can be adapted to suit the runtime. So let's take a look at the standard a bit more closely. So 61800 is split into 10 sections, plus the annexes, and it's just shown below there. But for this seminar, we're just going to focus in on section 4, so designated safety functions. The rest of it is fairly normal. It will sort of cover the periphery of the actual main subject, but we're going to look at this, as I said, the safety functions, which I think is probably the most important part of it. So safety functions in detail. So this is directly out of the standard. So in most cases, the safety functions of the PDS are a part of the safety functions of an application. Therefore, the safety functions are named safety sub-functions in the document. So this figure here just shows an example of a safety function, no different to what you're probably used to. So you've got your input, door switch or light curtain, some form of logic, safety relay, safety PLC or so on, and then the output. So the output being, in this case, we're actually talking about the drive, whatever that might be, whether it be servo, inverter, or whatever it is now split down into 3 further subsections. So stopping functions, monitoring functions, and output functions. So stopping functions are found on almost all machines, as you'd hope. But of course, they're split down into 3 categories, which again, you're probably familiar with from 60204, so 0, 1, and 2. When we relate this to drive systems, you can see the comparison table there of how that reflects in terms of the actual types of safety function available on drives. And these are obviously specified in 61800 as it shows there. I'm going to break them down in a little bit more detail as well. So safe torque off. Safe torque off is a term that's used very widely now, a lot of familiarity with that word. However, it does get used in the wrong context and can be very easily misunderstood in terms of how it's used. So in this case, safe torque off is the power generating energy supplied to the motor is safely removed so that no further movement is possible. It's not necessary to monitor standstill in this case. If an external force effect is to be anticipated, additional measures should be provided to safely prevent any potential movement. So this is where we start to talk about mechanical brakes and braking forces or locking off. So classic examples are vertical axes or applications with high inertia. So this safety function actually corresponds to a category 0 stop, so an uncontrolled stop. So in accordance with IEC 60204, if the function is triggered during operation, the motor will run down in an uncontrolled manner. So this is not desirable, obviously, in practice. And that is why the function is generally used as a safe restart interlock or in conjunction with the safety function SS1, which we're going to look at next. So safe stop 1, and again, these definitions are quite vague in the standard I found, and this is why we're going to expand on that a bit here. So this information hopefully will be of some use. So define motor braking is part of the safety function when the motor is at standstill, so the STO function is triggered. The safety function corresponds to a category 1 stop in this case, as a controlled stop in accordance with 60204. So the safe stop function monitors controlled braking of the axis directly within the servo amplifier or drive once the set braking ramp has run its course. The drive is shut down safely, the reaction times are reduced compared with the external monitoring solutions, and as a result, in many cases, the safety distance to the danger points are also reduced. So of course, this provides a number of benefits such as improved ergonomics for the plant operator, space savings due to the reduced distance between the guards and the danger points, and last but not least, there's cost savings obviously associated with that. Safe stop 2. So with safe stop 2 or SS2, defined motor braking is again part of the safety function. When the motor is at standstill, a safe operating stop is triggered. Unlike safe stop 1, the motor at standstill is in a closed loop operation. This means that the standstill position is held precisely, so it's active. Due to the active control loop, and of course this safety function corresponds to a category 2 stop according to 60204. So it's a slight difference, but you can see what that difference is hopefully. If the axes no longer need to be shut down at standstill, they'll be actively held in the current position, so the synchronization between axes and process is no longer lost. As a result, the axis can be restarted immediately at any time, which clearly increases the plant availability. So here too, the drive integrated function leads to short reaction times. So this minimises the associated risks. So the monitoring functions and response times have a direct influence on the potential channels available until a safety shutdown occurs. As the reaction times are used in the calculation of the safety distances, the benefits listed for the safe stop function 1 will also apply in this case. So now we look at the monitoring functions. So modern drive solutions not only examine how axes are switched on and off, but also look at the potential risks that may arise during the operation of the axes. So the functions employed to avoid and reduce these risks are summarised here under the heading of safe monitoring functions. Safe operating stop. So the safe operating stop monitors the standstill position while the motor is in a controlled loop. Once the safety function has been lifted, the production of the machining process can be continued with no loss of precision. This function is generally used in combination with a safe stop 2 function, as a standstill monitoring usually involves a braking process. So a typical situation would be access to a danger point during process intervention. An operator stops production using a command such as stop at the end of a cycle, for example. Once the plant is stopped, the safe operating stop function is activated, after which the guard locking device on the access gate is unlocked, and the plant can now be accessed without any risk to the operator. So we can now look at safely limited acceleration, or SLA, safe acceleration range, SAR. And again, these aren't terms that get used very often, but need to be considered. So safe limited acceleration prevents the motor from exceeding the specified acceleration limit. Safe acceleration range keeps the motor acceleration and or deceleration within specified limits. So we'll look at safe limited speed. Safe limited speed is probably the one that you have all heard of, quite commonly used. Again, in practice, this safety function is often applied as safely reduced speed. As a result, a defined transition from the operating speed in automatic mode to the reduced speed in setup mode must be guaranteed. If the monitoring function detects that the limit value has been violated, the drive must be shut down safely. So the manner in which the shutdown is achieved depends on the application. So it's best to aim for defined braking using the SS1 function, followed by removal of the power generating energy. So just different versions of a very similar theme, just depends in which order you apply them. So safe speed range. The safe speed range can be used to monitor a safe minimum speed. For example, again, the reaction that occurs when a value falls below the stated limit. The value depends heavily on the application. Drive axis may be coupled, in which case an appropriate reaction must be triggered when shutting down the drive. So a selective shutdown in this case. So SSR can generally be used for permanent process monitoring. Risks cannot always be eliminated by just limiting the capacity for speeds to suddenly increase. So speeds that reduce suddenly as a result of a fault can also present a risk and need to be considered in the same way. Safe limited torque and safe torque range. So like acceleration monitoring, the problem with torque or force monitoring is a lack of suitable or established sensor technology to carry this out. Torque measuring systems are not widely used on standard drives, but servo drive technology provides the option for indirect measurement via the motor current. So the relation between motor current and torque obviously being used. The motor current is proportional to the motor's force or torque, so the hazard resulting from a hazardous movement is limited. Safe limited position and safe limited increment, and it's as I said before, you will get a copy of these slides. There's a lot to remember in terms of acronyms, but it's important to understand these different headings. Safe position monitoring ensures that the motor does not exceed a preset position limit value. If a limit value is violated, the motor is braked using the safe stop. The stopping performance achievable from a technical point of view must be taken into account. Below the limit value, there are no restrictions in terms of acceleration or speed of the motor. Absolute position detection is required for this safety function. So absolute encoders may be used, or relative measuring systems may be combined with a safe reference run. Safely limited increment. The motor is allowed to travel a permanent distance following a start command. A safe stop function must be triggered once the limit value is reached. If the permitted distance, is exceeded, this must be detected and the drive must be safely brought to a standstill. Encoder systems with relative measurement are sufficient for this safety function. Safe direction. This prevents the motor from moving in an invalid direction, as the name suggests. The safety function is frequently used in combination with safely limited speed, for example, maybe in setup mode. So here too, the drive integrated solution enables the fastest possible shutdown. Safe cam and safe speed monitoring. So safe cam, another one that's not used very often, or certainly not spoken about much. A safe output signal indicates whether the motor is positioned inside a specific range. These ranges are absolute position windows within a motor rotation. The basic function involves safe monitoring of absolute positions, which is why appropriate sensor systems must be used. Safe speed monitoring. The safe speed monitoring safety function is very closely related to safely limited speed. However, if a limit value is violated, there is no functional reaction from the components that are monitored, merely a safe message which can be evaluated and processed by a high-level controller. So on one side, the controller can perform more complex reaction functions, while on the other, the safety function can be used for process monitoring in this case. So the output functions, well, we're going to look at those. They're dealt with in functions related to holding brakes. We'll summarize this under safe braking functions. So we'll look at that a bit closer in that section. So safe brake control, and again, this is one that gets overlooked in terms of it might be used, but certainly the fundamentals that need to be adhered to are not. So safe brake control, SBC, supplies a safe output signal to drive an external mechanical brake. The brakes used must be safety brakes in which a standby current operates against a spring. If the current flow is interrupted, the brake will engage. So it's fail-safe. Control modules frequently include a power reduction feature when the brake is released to reduce energy consumption or brake heating. A safe brake test may be required to detect faults during operation, depending on the risk analysis. We'll cover that, the safe brake test, shortly as well. Holding brakes or service brakes often used on axis with suspended loads alongside the brake. The brake drive is another key component in terms of the safety function. So the safe brake control function is normally initiated in conjunction with the safe torque off safety function. Again, so safe torque off appearing once more, but it just shows you where or how it should be used in conjunction with other aspects and not just on its own. So safe brake control will influence the entire brake management of the drive axis and should be coordinated with the purely functional requirements as well. So safe brake test. Now, just a note there, it's not referenced in the standard. Mechanical brakes are often used as standard components in safety functions. In this case, the user must carry out a safety assessment and obtain confirmation that the brakes satisfy the requirements relating to the performance level or the safety integrity level that's required. So this is again back to risk assessment. We always say this about just about everything that we talk about, but this is how it should work. So the safe brake test checks the function of the brake. The brake test basically should be carried out again based on risk assessment. This can be every shift, so every 8 hours, for example, or after each production cycle, but just depending on the hazard that's actually presented by that suspended load, for example. So it's down to risk assessment as to how often that should take place. But something that should certainly be considered due to the fact that you'll have parts that wear over time. And then of course, if eventually it does fail, and it may possibly fail in an unsafe manner in this case, then it could cause quite a lengthy downtime. Which can be easily avoided if the brake test is implemented. So now I'll look at a few examples, and again, it's just a graphic example of where maybe some of these aspects will be considered. So we've got the setup there of safely limited speed. So this is something that can be set according to the process. The maintenance safe brake test we've just been discussing there, and you probably can't see it very well. I just about can, but basically you've got a vertical load there. Just the example there of where that could be tested. There's certainly more hazardous eventualities of suspended loads that I can think of, but that's one example. We've got safe direction there being used for muting, just to ensure that everything is operating in the correct way. And then again, I would expect that you'd probably quite easily assess there that if it goes the wrong way, then you potential collisions and potential trapping points and so on. And then we've got the operator intervention or safe stop 2. So this is where we ensure that everything has come to a standstill and is monitored before the operator accesses the hazardous area. Maybe unblocking a jam or adjustments or whatever may be required. So we'll look at some application examples, and yes, there's some examples of product, of course there is, and there's various different products on the market that look at the external from drives. So basically, you can look at and again, some of the drives have got some of these built in, but it's not that often that you'll find that. So people do prefer to use external devices. So in this case, we've got standstill relays. So in particular, back EMF is a good way of monitoring standstill. It's non-invasive. There's no sensors required other than just monitoring the voltage. So that's really quite a good easy way of monitoring for standstill. Speed monitoring. So if we now start to look at safe limited speed and this kind of things, you can start to specify quite a lot of speed ranges, underspeed, overspeed, this kind of thing. And then you've got the Pilz multi extension monitoring modules, so they can just be added to a Pilz multi and used accordingly. So again, there's different types. So there's a flavour for every requirement. So you've got something maybe if you're a low level safety requirement or high. So you have 2 proximity switches or a single or encoders. So it covers quite a wide variety of applications there. And then the PSS 4000 speed monitoring modules in the same way, where there's different modules available for different types of sensor. I've put this in here again because if you're talking about safe stops and safe speeds, then certainly mode selection features in there as well. So there's a range of products that cover that as well. So that's just there purely for reference when you get the slides. Again, a product you may not be aware of, but you can obviously the safe access and safe mode selection. Again, a very wide range of products there that can be used. So back on track. So with safe speed signals, we start to look at the sensors that are used. Now, there's tons and tons of different types of encoders out there, proximities and the like. And there's just an example there of the different types of encoder signal and how they're used and how they can actually be used to achieve ultimately a higher level of safety in most cases. So most encoders don't achieve the universal dual channel structure, but there are some now available, and so where there is a strict diverse dual channel design, you can achieve up to SIL level 3 performance level E, for example, in accordance with 61508. So it's not easy to do sometimes, but you just got to be aware of the types of signal and how they apply to the individual applications. So again, another example of the type of encoder, how it's used, the different types of signal and how they apply, and then the safety integrity level that can be achieved accordingly. So it is something that needs to be considered, and we're more than happy to get into discussions about that should you have an application that requires that. So just a few examples there. So now we'll actually look at the applications themselves. Now this is just purely examples of an arrangement, if you like, of how this would be used. So in this particular case, sensor evaluation is undertaken, for example, by a small safety related controller, which activates the safety functions in the drive for a safe I/O connection. So it is a safety drive. The servo motor has an integrated sine cos motor encoder for motor control and positioning. So the reaction time before the safety function is activated is around 60 milliseconds. The reaction time when the limit values are violated is less than 10 milliseconds. So a very fast reacting system in this case due to the closed loop. So safely monitored drive with frequency converter and asynchronous motor, so it doesn't have to be a servo. An incremental encoder is used to detect motion. A safety relay or small safety related controller with motion monitoring evaluates the sensor signals and triggers a safe talk off function in the event of a fault. So again, this is fairly common, I would expect. Safe stop function. So the safety function e-stop, when the light curtain is interrupted, is addressed here. It illustrates a safe stop function for a motor driven axis. So this example uses a light curtain, a configurable safety controller and a servo amplifier with integrated safety functions. A servo motor with feedback system is connected to the servo amplifier. So the risk analysis permits a stop category 1 for the axis in this case. So safe stop function on a vertical axis. So building on the safe stop function example, a brake is added to the structure, as you can see there. So holding brakes and service brakes are also both quite common when this is being used. Jog function with safe limited speed. So this is potentially where you would find that mode selection, for example, would be used in order for this to be allowed to actually happen. So it may be an enabling switch or something that actually initiates that. So jog functions can generally be carried out while guards are open. So obviously this needs to be monitored very carefully. And then the respective application will determine the type of increment that can be classified as non-hazardous. And in this case, it might be useful to consult a few other standards there, 13854 and 13855. So external motion monitoring with one standard encoder. In this example, one standard encoder as a sensor is responsible for motion detection, and various combinations are possible in conjunction with the drive controller. The hazardous function is shut down via a safe talk off function, which is already directly available within the drive. If it is only the monitoring device that evaluates the encoder signals for the safety function, i.e. the drive controller does not use an encoder or only uses a separate encoder, a maximum of performance level C can be achieved. So something to bear in mind there. This requires an encoder with the mean time to dangerous failure equaling high and classification as a well-tried component or category 1, alternatively direct classification as performance level C. So here we have a bit of a combination. So external motion monitoring with standard encoder and a proximity switch. So generally 2 separate sensors for motion detection are required in order to achieve the highest performance level with standard sensors. So depending on the external monitoring device, these may be 2 encoders, 1 encoder and an additional proximity switch, for example. The encoder signals evaluated by the monitoring device for the safety function can also be used by the drive controller for speed and position control. The following safety functions are possible with the illustrated configuration. So the safe limited speed, safe direction, safe operating stop, safe speed range, safely limited acceleration and safe acceleration range. So quite a lot can be covered very simply with this arrangement, which is gives you a lot to play with in various different applications. So it does really, the safe functions that can be realized depend on the monitoring functions implemented in the external monitoring device. So it does depend how this is approached. External motion monitoring with 2 standard proximity switches. So without an encoder, safety related motion monitoring can still be implemented using standard sensors in the form of proximity switches. And again, even up to performance level E. But again, the guidelines must be followed in terms of how the proximities are arranged. So one of the proximities will always be, the signal will always be high on at least one of them in order to achieve the dual channel monitoring required. So as in the previous example, 2 separate proximity switches are required for motion detection. The following safety function is possible with illustrated configuration. So safe limited speed and safe speed range is all you can achieve there. But again, this is quite common and quite widely used. So again, the little footnote there, I read that once, so I won't read it again. External motion monitoring with a safe encoder. So now we are actually using it's classified as a safe encoder. It's got the approval there. So in this example, the hazardous movement is shut down via the STO function available within the drive. and again, the following functions can be implemented with this illustrated configuration. So because of the encoder and the type of signal, so the ABZs, you've got direction, you've got speed, frequency, everything's there. All of these safety functions can actually be carried out. So again, safe limited speed, safe direction, safe operating stop, safe speed range, safe limited acceleration, and safe acceleration range. So again, you don't have to use all of them, but if your application demands it, then they're available. So one of the shorter webinars, I think you'll agree, but we'll just summarize what we've gone through there, and bear in mind we've only covered part of that standard, and I think it's the most important part, but again, it's just a beginning to look into it. Yeah, I think the statement "more than safe talk off" says it all really. It's not just about the STO, and this is the thing I hear all the time is safe talk off. We'll put safe talk off and that'll make it safe. No, it doesn't necessarily. Very few applications does safe talk off actually meet the requirements of the standards. So in this case, it's always best to actually look into this in a bit more depth. Is braking required? Does the inertia need to be held in order for it to be safe? And certainly where safe speed monitoring and safe speed is being used for loading or as part of the process and in interaction with the operators, it's extremely important to consider these aspects. So I think it's important to note that while safety functional drives can be of great benefit, they do not represent a complete safety solution. The entire system must be considered when assessing the overall safety, and that's pretty much what I'm trying to drive at there. Excuse the pun. So thank you for listening. Now, of course, you can access all the previous webinars and basically on this link here. The next webinar is October the 14th, and we'll cover safe human robot collaboration. And yeah, there's another link there for the future webinars. So please keep logging in, keep registering, and we'll hopefully speak to you soon. So thank you for listening.